All right, so PID loop systems or PID control loops. The idea here is that as again we're closing the loop, so we're going to use a sensor to monitor one or more values and feed those back into the feed them back and into what we call a summing junction. And so here's our summing junction here. All right, so we're going to take the output. So we're monitoring this output. Now, and this is a pretty simple example because we only have one output that we're looking at, and in a true industrial sort of application, we're going to have lots of different values that we're going to be monitoring. But we're going to take those, we're going to feed those back into our PLC. We're going to have a set point. That's where we want the value to be. And so we're going to generate, wrong one. So we're going to generate this error, which is the difference, the set point minus the process variable value. So that the error or the difference between where we want to be, the value we want it to be at, and the value it's currently at. All right. And so then we're going to feed that into our control system and then output that through our actuator or our control device and then into the actual system. So I guess this slide really should have another box here. So this section here is our control, and we're putting that all together. And I guess what this says control device, this is the device we want to control, or our system. Okay. And so I don't really have like the actual actuator, whether it's a motor or a valve or servo motor, heater, whatever it is that we're trying to actually control or trying to drive the system with. But we're feeding the control signal. So U here represents our control signal. And this is the system we're trying to control, and then we have that feedback. All right, and so the idea of what we did like last week was we did proportional control. So we just had this P part, and all we did was we took our error and multiplied it times this error, and multiplied it by a gain. So we took the error and we multiplied it by some amplification factor. Okay, so we normally call it a gain, but we're just amplifying it, or maybe we're reducing it if your gain is less than 1, but if your gain is greater than 1, you're amplifying this error and then feeding it back into the system. Okay, and I actually was doing this yesterday and the video, and I kind of had here is our system. Okay, and so this is the response of the system. Okay, so the black here is open loop. So we haven't, all we did was the system was at rest. It was sitting down here doing absolutely nothing. Okay, so the system was at rest, and we turned the system on, and the set point was 5. Okay, so our set point over here was 5. This is where we're telling it we want it to go. And with this particular system, open loop, we told it to go to 5, and it goes to 5. All right, but we had very little resistance. Okay, we only had 1 ohm resistance in this example, so it's a small resistance, and so it actually overshoots 5 and then comes back down. It goes a little bit below, and then it comes back up. I'm exaggerating it here just to make it a little more obvious. and then it finally does settle out at 5. All right, and when we look down here, this down here, the black down in the bottom, is the amount of energy that it takes. Okay, and so this entire black area, this is how much energy. Remember, energy, when we calculated energy in the integrator lab, right, we took the time times whatever value, right? So this is our control out. So how much energy did it take us to get that? Well, we're driving it, and this is how much energy it takes. Okay, so it's 15 seconds times 5. All right, so that's let's see, 30, 60, 75. So it takes 75 units of energy to drive the system. All right, and that's just to drive the system, but we have no control over the system. And so what that means is if there's a disturbance into the system, we can't do anything about it. Okay, so if there's disturbance in the system, we have no control. We told it to go to 5, and it goes to 5, but we're not giving it any, we're not feeding back. So if some external force drives it greater than 5 or less than 5, we have no control going on here with this open loop. So then I went in a proportional control. So I did the proportional control with a gain of 1. And when you see that, you see that, hey, this control, by putting this control in here, it actually, I end up, looks like I get a little bit more overshoot. Okay, so from the final value, remember the overshoot is always the final value that it goes to. Now remember, I wanted it to go all the way up here to 5, but in reality it's only going to maybe 1.8, right? It's nowhere near the 5 that I wanted it to be at. But also notice the energy, the amount of energy that it took right down here. It didn't take as much energy as it did with open loop. So by closing the loop, I got the system to move and I used less energy, but I didn't get it over to where I wanted it to be. All right, so what I do next now is I'm going to increase my gain. So I'm going to double my gain to 2. And so now you can see that, notice the system starts moving much faster. Okay, so the system starts moving faster, and then it starts going up here, but it ends over here. So again, instead of going all the way up to 5 where we wanted it to, it actually only goes up to, let's see, this is 2 here, so it's going above 2, so I don't know, about 2.3 or something. Okay, so, and it uses all of this energy. All right, now notice it's using all of this energy to get there. It got a little closer to where I wanted it to be than it did with a gain of 1, but it just didn't make it. So I tried increasing the gain again. So I increased the gain to 4. So I increased the gain to 4. And now notice, boom, right here, it shoots right up here, and it actually gets about to where I wanted it, but then it drops down again and it bounces around more than ever, and it still only makes it up here somewhere around 3. Okay, So it does still not getting, I still have the huge amount of error, steady state error. This is the difference between where I want to be up here at 5 and where I end up at. Okay. And look at all the energy it takes. Okay. So when we look at this, this is all the energy it takes. All right. So notice it's driving it all the way up to 20. So it's taking a lot of energy, and yet it didn't get there. All right. And as I talked about in yesterday's video, the problem with this, how much energy this is taking, is the fact that my controller can't output more than 10 volts, right? So if this is a voltage here, if this control out is a voltage, my digital to analog converter maxes out at 10 volts, which means that putting a gain of 4 in there, this is what my control is going to calculate that it needs to do, but it cannot output that because my digital to analog card can't put that much energy out. All right. And even with this much energy, even with all this energy here, I still have a lot of steady state error up here. All right. And so when you do nothing but proportional control, you're going to have steady state error in the system. It's just guaranteed. Okay. Anytime you do straight proportional control. Now, the advantage here, you might be saying, why, well, what good is this? Well, the good is the fact that even though we have steady state error, we have feedback. So that these control systems, if some disturbance comes into the system and starts trying to push the system, these control systems, any of these 3 gains, assuming we had enough energy, I guess, anyhow, but these control systems are going to try, after the disturbance goes through, they're going to return it back to these final values, whatever the final value is. Okay, depending on our gain. All right, so if a disturbance comes in and it pushes the system, these are closed loop systems. Okay, well, they're the same system with different gains, but these are all going to return it back to those values. So that is the advantage of the proportional control. Even though it gives us a steady state error from where we wanted it to be, we have closed loop bonds so we can react to disturbances. And so it will still, if a disturbance comes in and starts pushing the system around, this control system is going to push it back to where we want it to be, minus the steady state error piece. As I was saying before, hopefully you caught all that, was the fact that if we are going to do just proportional control here, then we're pretty much guaranteed that we're going to have steady state error. All right. The only way to get rid of steady state error with nothing but proportional control would be to drive your gain so high that in reality it wouldn't be able to do the job anyhow. So you're always going to have some steady state error if you just do proportional control. So if we add an integrator, and we know how to do that, we've done that already just for integrating. The only difference here is what we're going to integrate is the error. All right, now remember what happens when you're integrating is you keep adding and you keep adding and you keep adding and you keep adding. So what that means is that if your error is I don't know, just pick a number, easy number, 1. Okay, if your error is an error of 1 the first time you go around the loop, so the first time we go around the loop and our error is 1, and so what this is going to do is the integrator is going to remember that. See, the proportional control, it totally forgets, like when we go around the second time, it totally ignores the fact that we had error the previous scan. All right, it doesn't pay any attention to that. But an integrator, what it does is it remembers, hey, I had some error last time around. All right, so I know I had some error, and I remembered what that error was. And now, as I go back around, I have more error. And so there's even more error there. And so I'm going to add those two together. And now so the error keeps adding up and adding up and adding up. And so what we have to do, or what the integrators basically does for us, is it remembers that and it keeps building and building and building. And what that's going to do is allow us to push that system. So when the system has a lot of error, the integrator is going to say, hey, here's a bunch of error. Next time around, I'm going to push it a little bit more because it's not getting up to that steady state value. And then the next time around the loop, it's like, I still have error. Maybe it's a little bit smaller because I pushed you harder last time, but I still have error. So I'm going to push you a little bit more. And it keeps doing that every loop. Push a little more, push harder, push harder, push harder, until it drives the output to the set point. All right, so we're driving that output to the set point. So what the integrator is going to do is it's going to drive your error to 0. Okay. Now, of course, the problem with that is the fact that if our system can't push it that hard, then it will actually it can't do it. Okay, so if you're trying to push it to 0, but you just can't push it that hard because you don't have enough drive in your control system to drive it that hard, then you're never going to get that. So you're always going to have some steady state error. So when you build your system, you need to make sure that you can drive it to the set point. Okay, however much energy that takes. Otherwise, you're never going to make it to the set point, or you got to lower your set point, I guess. So like one of the examples, and I don't know how much we'll do it next week in class, in the lab, but if we try to like drive the RLC system that I talked about last time, if we tried to drive that up to 10 volts, well, our output only output 10 volts. And so we can't really do it. If you do a closed loop control, you can't drive it all the way up to 10 volts. So we end up like driving it to 2 volts instead of 10 volts so that our system can actually do it. All right. But the point of the integration here, the integrator, is it will remember the error and it will respond to that. It'll basically keep adding those errors up, and they'll build up and build up and build up until it actually pushes the system hard enough to drive the steady state error to 0. All right, so that's why we want an integrator. So a lot of times what you see is people do a PI controller. They don't do the derivative piece, they just do the proportional, because the proportional, as we saw before, the proportional will get the system moving pretty fast. But what the proportional causes is that error. Okay, so it causes that steady state error. So if we add in the integrator, by adding in the integrator, we can drive the error to 0. Okay. Now, the derivative piece, on the other hand, it works the opposite direction that the integrator does. Remember that an integrator looks at the area under the curve. What a derivative term does is it looks at how fast the system is changing. So All right, so if you remember from the integrator lab, we had some system that was bouncing up and down like this, okay? And when we did integration, what we would do is we kind of went in here and we set up this delta T. All right, so we set up this delta T here, which is the difference in time, right? So this is time over here, probably in seconds or even milliseconds. And so at each one of these, okay, I'm just hand drawing it so they're not nicely laid out. But when we were doing integration, right, we would have, this was power in our integration lab, right? And so we had, this was power 2 and this was power 1. And we had our delta T, each one of these is a delta T. And so we used a timer to do that. So when we do integration, you are going to have to use a delta T timer. Now, if you look either in the function block programming or even in the ladder logic, they actually have a PI controller and a PID controller. All right. And so you could actually use those blocks to do your control. But, you know, and basically part of what those blocks would do is they would do a delta T for you. It's supposed to be a T there. They kind of have a special timer dedicated to that. And so there's a timer section that you would set. One of the settings in this block, you would have to set the timer. All right, but remember, so we had power 2 to power 1. Oh, I didn't realize it erased the whole thing. I just wanted to erase one little bit. All right, so we have here time. This is why I never use this one. And so we have this power 1 and power 2. Just kind of draw them out a little bit further here. All right, and so this is my delta T. And then we would, to calculate the area, to do the integration, we would have to take, calculate the area. We would calculate all this area. So this would be 1/2 power 2 plus power 1 times time, right, which was seconds. All right, and this is your integration piece, right? And we did that in class. This should really be time here, or time delta T. Okay, but if we're going to do derivative, okay, a derivative is looking at a derivative is looking at how fast the system is changing. So if you look at point power 1 and power 2 here, you see that this is going up really fast. Okay, so if you look right here, we'll call this section 1. Okay, at section 1, it is increasing. Section 1 increasing. I'm sorry, that is not writing very well there, but it's increasing fast. And so we calculate how fast that is, how fast. So the derivative is equal to, it's like the slope we've been doing and all the scaling we've been doing. It's power 2 minus power 1 divided by delta T. So we still have this delta T piece here, but you know, so this is a really positive. This is number one, it's a positive direction. and it's really big, okay, very big. Now, on the other hand, if we look at what happens right about here at this time, so now if we look from like here to here, you see, remember, this will become our new power 2, and this would become our new power 1. All right, and so for this one, for section 2, here, it's almost constant, okay, very little change. So there's very little change there. And so, but we would calculate that, okay, and let me just kind of mark these with a prime here. Okay, so this this derivative at this point in time, it would be power 2 prime minus power 1 prime divided by the delta t. All right, and so that's we'll say it's about even. Okay, it's not changing very much at all. Might have went up a little bit or something. Now, do one more here. Now, if we look at green, okay, this becomes P2, and I'll call this like P2 bar, and what was P2 is now P1 bar. All right, and so now what we're doing is we're looking at how fast it's changing. So now this is section 3, okay, and for section 3, we get that it's going down fast. Okay, so it's going down fast, and so it's going to be this P2. So the derivative piece is P2 minus P1 bar, so P2 bar minus P1 bar divided by the delta t, and this value is going to be negative, right? Because P1 is bigger than P2, so this value is going to be a negative value. And that's telling us that the system is going back in the opposite direction. All right, and so a derivative is looking at how fast the system is changing. All right, so, but anyhow, so we, I just wanted to try to explain out to you the different pieces of the proportional, the derivative, and the integral. Integral or integration, pretty much exact same thing there. All right, so now the proportional piece here happens every scan. All right, so you all it does is just multiply the proportional piece multiplies this gain times the error every scan. That can happen every single scan, and then make an adjustment to go out. The integrator and the derivative, both of those have that dt there. You see the dt in the slide there for I and D. Those are delta t's, so that you've got that timer action. So those are only going to change every delta t. So and we can set that just like we did in the previous integral lab. But in the previous integral lab, we were just trying to add up energy. So we had something like, I think half a second, right? 500 seconds. That was fine for trying to calculate energy, but it's terrible for control, because I talked last week, in last week's lecture, I talked about the delay. Okay, so you have this delay built into a PLC or any type of digital computer-based control. You've got this scan, so you've got to read in the data, run through the code, calculate your outputs, and then send those outputs out. So it's very slow. But the so the normal scan time of modern PLCs, when I say slow, it's maybe a millisecond. So that's not too bad. But if you start when you try to calculate integration or derivative, now you've got to build in some extra time for this delta t piece. And delta t, I mean, you could actually just use delta t to be the scan. The problem is that we don't really know what the scan time is, and the scan time will change based on how much code you have. So the what we do is we build a special timer in there so we understand what delta t is. But the problem with that is that's adding extra delay. So we might make delta t, say, 5 milliseconds. And that's an extra delay built into the system, which can therefore drive the system into that instability we talked about. So the more delay you put in, right, now the system's reacting slower and slower. And so to changes, and because you have a bigger delta t, so the bigger you make delta t, the slower you are to respond to changes. And then what you're doing is you're reacting to something that didn't happen now or a fraction of a second ago. You're reacting to something that happened yesterday or last month, and it's too late at that point. All right, so, and I'm exaggerating, of course, but you need to try to keep delta t very small in your control, so that you don't build in too much delay. So, like I say, and it's this this the value of delta t depends on basically two things. Number one, how fast does your system change? Like if you're running a heater and you're trying to heat up this very large object, heater, it's going to take a while. So a half a second delta t might be perfectly fine, even a full second delta t, because it may take an hour to heat this thing up. All right, and so if it's a really slow system, it's not that big of a deal to have kind of a slow delta t. Um, but if it's a fast system, then you need to make sure the delta t is extremely fast. And the other aspect of it is how fast can your PLC do the work you're asking it to do. All right, so if your PLC has enough processing power to do everything, not just your PID controller, but you might be doing 3 or 4, 8 or 10 PID control with one PLC. Can it do all of that with the delta t that you're giving it? Okay, and various aspects like that. So the speed of your controller and how fast the system itself is going to respond. So if the system is slow, like I say, like a heater, or let's say that you're trying to fill up a water tank that a 2,000 gallon water tank, and you're trying to fill it up. It's probably, to take, if you're pumping, 30 gallons a minute in there, or even 50 gallons a minute, right? It's going to take a while to put 2,000 gallons in it. That's a slow system. All right. So it's okay if your delta T is a little bit larger. All right. So let's look at some responses. A lot of these slides are just saying a lot of what I've already said. Okay. So you can read through the slides, but I'm not going to sit here and read you the slides. All right. So I've got a few graphs in here where I'm trying to show you what effects these to a PID controller make. So if you look here, I have the blue line is my step response, and the step response is a step increase from where it was at. Now look at the numbers here. I guess it looks like it's going from about 0, and I'm stepping up to, I guess, a 1 there, but yeah, so the little gray line is a 1.1. All right. But so the blue line is our change. So at time t equals 1, I change from 0 up to 1. And I'm showing you with 3 different values of gain in here. Okay, so the purple is a gain of 1.6, and you see that I get a really big overshoot. So it goes up really, really fast. It overshoots, and then it comes back down, and it undershoots. It goes back up. It overshoots again. Then it comes back down, and it overshoots quite a few times before it finally settles out. Now remember, this system that I'm doing has an integrator. There is an integrator in it, and so notice the steady state error over here at the end, they all end up at my reference or my set point, okay, because I have integration in there. That's what's driving the error to 0. However, you can see as I change my K, if I decrease K from 1.6 down to 1.1, I get a little bit of overshoot. It drops down right here. It's just a little bit below. And then it finally settles out. So it's actually, with a K of 1.6, notice it was bouncing around all the way out here to 6 or 7 seconds. But if I decrease my K, notice it took it a little bit longer to get up to this value initially, but it just overshoots a little bit, and then it returns back, and right here at about 3 to 4 seconds, it's already reached the steady state value. Okay, so these are changes. The only thing I'm changing here is the proportional piece. So this is why we always want some proportional piece, because we can speed up or slow down the system for that. All right, but notice as we increase the proportional piece, we get a lot more oscillation. Okay. And then of course, if we decrease K all the way down to 1/2, okay, we're basically taking energy out of the system, or out of the control piece anyhow, and it's given us an overdamped response. Now notice over here, you notice this isn't a perfectly smooth line. It looks a little awkward here. That's because, remember, we're doing proportional control, integral control, and derivative control. So this kind of, I don't know if you guys can kind of see that, but it looks a little weird there. It's not like a perfectly smooth thing, but you got to remember that we have these other controller pieces in here that are affecting things. So so that's why it looks a little bit awkward there. Okay. All right. So again, the point of the proportional control is it gets the system moving faster, but as we keep increasing gain, we get much more oscillation going on. Okay. When we integrate, right, the real goal of integration is to drive that error to 0. So if I try to draw an integrator piece here, what it'll do is it will it slows the system down. So as you put the integrator in there, it slows the system way down. So the original system may have been pretty fast, but then when we get to the integrator piece here, it slows it down. Now what's interesting is once you put that proportional in there, sometimes you'll see a hump like this. And then the proportional or derivative control gives you this little hump over here. But then you can see the integrator starts driving that error over. And like I said, I'll try to do a better plot of these and get uploaded for you. But that as you increase your gain, you can also increase this hump and get it to respond a little bit faster. But again, the integrator piece normally slows the system down much more, and you get this, like, you can see the error going to 0, but it's going fairly slowly. All right, now the derivative piece, what the derivative piece will do is basically it'll try to take out the oscillations. Remember, with the proportional, we had a lot of oscillations. So if we add derivative, you tend to get a lot of overshoot with the derivative, but then it'll settle down faster. So you'll get like a bigger hump of overshoot, and it stays up there longer, but then it will it prevents all the oscillations. Or doesn't, I shouldn't say prevent, it reduces the oscillations, because remember, the derivative is looking at how fast the system is changing, and it tries to react to those changes. And so the derivative will kind of try to keep the system from bouncing back and forth or oscillating as much. All right, and so you'll tend to see, if you have overshoot in your system, you will tend to see a bigger, the humps, instead of like the red line here. The red line is going up, and then it's coming down much faster, but it's going down so fast now it's going below, and then it's coming back up. So you're getting these oscillations where, as I increase my derivative, you see that it actually takes it a little bit longer to get up there, so it slows down the initial response, and it keeps it up above longer, but it just dips a little bit below. So as you increase your derivative piece, you tend to get the overshoot to stay above longer, but you reduce the oscillations. And that's the advantage of the derivative. It kind of reduces oscillations, okay? Because it's reacting to how fast the system is changing. So it basically tries to slow down the changes. And so, like I say, you actually end up being over longer with a derivative as you increase the derivative gain. But it takes out the oscillations. You don't get it. You still have some oscillations, but it reduces the oscillations. Okay, so those are our proportional integrator things. So I tried to kind of give you a table here to summarize these. The first one here is just, this is what we called the bang bang controller, kind of what we did in the PLC1 class, with just a high sensor and a low sensor, and just turn it on or off, and that was about it. Okay, but then if we do proportional control, we can reduce our response time, and we can end up with a lot of overshoot. And I should add a oscillation kind of piece here into this table here, but we have a lot of overshoot, a lot of oscillation. Okay, and with the derivative, we maybe decrease the overshoot a lot, but we decrease the oscillations. Okay. Okay, so I'll just maybe put it there. So the derivative really is decreasing the oscillations. It has little to no effect on the steady state error. Okay, but it's the derivative piece really kind of decreases those oscillations. Okay, which means it'll actually, this is actually wrong too. It actually decreases the response time a little bit. All right, so that's kind of the summary there. Don't know why I have a blank one here, but this is just kind of showing, trying to chart that. This chart's a little hard to read, I think, though, so I wouldn't pay too much attention to that one. All right, so like I say, when you uh, when you do this in ladder logic, okay, so inside of your ladder logic, you can just build an integrator, a derivative, and that using ordinary compute statements. Okay, so where did my box go here? All right. So what we can do, if we're gonna, the first thing we would do is we would have a compute state, or we would have a compute statement to scale. We need to scale our input, right? Because our input is coming in as an analog signal, which is either something like a 0 to 10 volt value. And so, it's actually be 10,000 millivolts if you think about the compact logics we were using, or it'll be something like a 4 microamp to 20 microamp signal. And so we need to scale that back into volts or gallons in the tank or watts or temperature, whatever our process variable is. Okay, so that's the first thing. We would need a compute statement to scale that back in there. And then we would use another compute statement to calculate our error. Okay, so our error would simply be, right, our error would be the scaled process variable right? It'd be our process variable after we've scaled it up above. It's actually, sorry, process variable, usually it's going to be the set point minus the process variable. That's typically, remember, we could do process variable minus set point, or set point minus process variable. Okay, so that would generate our error. Then if we're going to choose proportional control, remember we usually use a U for control, so we would call this U proportional is going to simply be some proportional gain. A lot of times we use something like KP times that error. Okay, that's our proportional control. All right. Our so that would be a compute statement. Okay. Now, if we're going to do integration, right, we're going to have to let me just make a comment here before I go on. So this is going to be proportional control. This can happen every scan. You could just do it at delta t if you wanted, but all right. So then the next we're going to do integration. So when we do integration, we're going to have to remember that error. So we need to remember the error. Okay, so you're going to have your error plus error last. Okay, so you're going to have to do like a move first. I'm going to run out of room on this slide, but you're going to have to do a move, okay, to move error to error last, because you need to remember that. Okay, so your error is equal to your error last, and then your control now, integration. All right, this is going to be your last value, because you're going to remember this, plus, and now we're going to calculate that area. So that area is error plus error last times delta t dot preset divided by 2. Remember, this is a trapezoid. We're using a trapezoid to calculate the area there for that, and that's going to be our integration piece. And then we're going to do a derivative. Okay, so this was for the integration piece. Okay, and now we're going to do a derivative. Okay, now we already have error and error last up above. Okay, so we already did this move statement up here to get this. So now we're going to do this derivative piece. And this derivative piece, u derivative, is going to be error minus error last divided by delta t dot preset. Now, one thing, remember that delta t preset on a compact logic is actually in milliseconds. So we're going to have to add, we're going to have to also, divide this delta t piece by 1,000 to get it into seconds. Okay. And then we're going to have to add those. So if you're doing a complete PID controller, you're going to, your final output, your final control out is simply the sum of all these. So U proportional plus U integration plus U derivative. Okay, so there's your ladder logic. Okay, except for the fact that you need your delta t timer in there. But there's your compute statements to just use ordinary compute statements to do PID control. It's pretty easy. There's only a few lines. And again, if you don't want to do derivative control, you can leave this part out, and then you just have to remove it here also. Okay, so what do we got? I mean, this we're going to have to do anyhow. This scaling we have to do, all right? So we have to do that anyhow. This is just calculating the error. And then, you could combine this all into one great big long compute statement probably, or, well, you would still have to calculate your error and error last And you would really have to do the integration piece at least separate. But the others you could combine into a more complex compute statement, but it gets really convoluted if you do that, so I don't recommend that. Okay. All right, but that's PID control, and then so this right here, then you would have to scale this. I guess I forgot one more piece. We would have to do one more compute to scale this back into our output. Okay, so because we would have to scale this back into, four, I'm sorry, that should have been 4,000 microamps up there, right? So either, and 20,000 microamps. So, whatever, we got to scale this back for our analog scale back into, our digital to analog converter settings to send it back out into wherever it's going. Okay, so we're gonna have to scale that back. So I almost forgot that bit. Okay, and again, you might be able to do that scaling at least up in this where you add these three together, right? So this would be a compute statement up here. Okay, to add it all together. All right, so shrink it down a little bit so it fits on the slide there. But so that is our instructions, everything that we're going to have to do inside the ladder logic for our PID controller. And again, this is just doing ordinary ladder logic that we've already discussed everything. We've talked about all these. But if you look, like I said before, if you go up into the menu objects and look, they actually have a block, a PI block. And then in that PI block, you're going to have to put in values like the gains, right? So here, here was this gain. I forgot the gains too. So let me, let's put in big purple gain or something. So this was the proportional gain. Down here at the integration piece, it doesn't matter where you put the gain. I could put the integration gain, KI, would be here, or I could put it up here, either way. And then this one here, I could do the KD gain. So if we're going to do that, I guess we could actually just remove this piece and just put the KP down here and be done with it. And so I wouldn't need this compute statement. I could just add it right here to this one and do the KP times piece right there. Okay. So then this guy could go away. And that could be our proportional gain. Only thing is I'd have to multiply it times the error right here. All right, so this would be my PID control output right here. Okay, pretty simple to do, but like I say, they do have blocks where you can just go drop the block and bring it down. But inside of that block, you're going to have to define KP, KI, KD, and the delta T, the time, and there are probably some other settings in there that you can set also. All right, so, but that's pretty much it for PID. I will be putting a homework out there for you to work on, asking you different questions about it and things like that. So do you guys have any questions